Okay, let's discuss this practice exam. The first problem, we have fx, gx, and h of x. We are going to evaluate f compose g of f. By definition, it is equal to f of g of 5. So you're going to evaluate g of 5 inside first. G of x is 2x minus 1, so g of 5 is 2 times 5 minus 1. 2 times 5 is 10, 10 minus 1 is 9, so you're going to have f of 9. 9 is g5. And f of x is square root of x, so f of 9 is square root of 9. Square root of 9 is 3. So the first answer for part 1 is 3. And for part B, hgf of 9 is h of g of f of 9. So f of 9, we're going to always evaluate from inside to outside. F of g of h of g of f9, f9 square root of 9, we know it is 3. Square root of 9 is 3. And g of 3, 3 times 2 is 6. 6 minus 1 is 5. So g of 3 is 5. H of 5 is 5 squared, 25. So part A has answer 3, part B has answer 25. Okay, second, we have function fx equal to 1 over x plus 2, and g of x equal to 4 over x minus 1. We're going to find the composite function under the domain. Okay, so composite function f compose g of x. All right, f compose g of x. What is the meaning of it? The meaning is f of g of x. All right, this is abstract computation. G of x is just 4 over x minus 1. So it's a 4 over x minus 1. Right? You just replace g of x by 4 over x minus 1. And f of x is 1 over x plus 2, so it is 1 over, you just replace x by 4 over x minus 1 and plus 2. Right? So this is simplified. You multiply top and bottom by x minus 1. So the numerator, 1 times x minus 1 is x minus 1. Denominator, you multiply it by x minus 1, it's a 4 plus 2 times x minus 1. Check here, I multiply top and the bottom by x minus 1, both. So this cancelled with this denominator, you only have 4. 2 times it, you got 2 times x minus 1. Simplify it, you will get x minus 1 over, this is 2x minus 2 plus 4 is a 2x plus 2. 2x plus 2. All right, so this is the composite function. What is a domain? Domain, first, you have to make sure g of x is defined. First, the domain, x cannot be 1. Okay, x cannot be 1. And then this number, this input cannot be negative 2. How do I get negative 2? When x is negative 2, the denominator is 0. So this input cannot be negative 2. So this is 2 conditions. This condition is already clear enough. Here, this one, we multiply 2 sides by x minus 1. And this is 4 is not equal to negative 2x plus 2. So I move negative 2x to the right side. 4 move to the left side. 2 minus 4 is negative 2, so x is not equal to negative 1. See here? So the domain is the set of all x. X is not equal to 1, and x is not equal to negative 1. So this is the domain of the composite function. This is the formula of the composite function. And part B, we have G compose f. G compose f of x, by definition, is G of f of x. which is g of f of x is 1 over x plus 2, which is 4 over, you see, this whole thing will replace x, so it's 1 over x plus 2 and minus 1. And then I'm going to multiply top and bottom by x plus 2. Top and bottom. Numerator, it's 4 times x plus 2. Denominator, this whole thing times x plus 2 is 1, and minus 1 times it. All right, so it's a 4x plus 2. You don't have to multiply it. If you multiply it out, it is going to be 4x plus 8. Here is a negative x and minus 1. Negative x minus 2 plus 1 is minus 1. Okay, this is a formula. And what is the domain? Domain, you see here. The function f makes sense. So x is not equal to negative 2, and this is always end. And this whole thing is not equal to what? G of x. Where's g of x? G of x here. It cannot be 1, because when input is 1, the denominator is 0. All right, so this means we multiply two sides by x plus 2. 1 cannot be x plus 2. So move to the other side. X cannot be negative 1. You see, you move 2 to the other side, it's negative 2. 1 minus 2, it becomes 1 minus 2. 1 minus 2 is negative 1. So x cannot be negative 1, x cannot be negative 2. So the domain is the set of all x. X cannot be negative 2, and x cannot be negative 1. This is always end. Both are removed. Both cases are removed. Okay. Formula under the domain. All right, then let's check 3. 3, we're looking for the inverse of the function fx is equal to square root of x plus 2 and minus 3. To look for the inverse of the function, basically first you set y equal to fx. Y is equal to this whole thing. And then you're going to solve x in terms of y. So we move 3 to the other side. And square root take square of 2 sides. And move number 2 to the other side. Okay, so far we solve x in terms of y. And then we're going to exchange x and y. We exchange x and y. This becomes x plus 3 squared minus 2 is equal to y. So the inverse function is equal to this whole thing, is equal to this y. So x plus 3 squared minus 2. Right? So that is the inverse of the function, original function. You must do the exchange step. Okay? So next, problem 4. We have the function f as -1, 5, 0, 0, 2, 6. We're looking for the inverse. What is f inverse? F inverse is just simply exchange those two coordinates. This is -1, 5. The new one will be 5, -1. 0, 0 is just 0, 0. 2, 6 is 6, 2. This is an inverse. And f inverse of 5. F inverse of 5 is -1. You see, f inverse of 5 has value -1. F inverse compose f of 2. You see, f of 2 is equal to 6. F maps 2 to 6. F inverse maps 6 to 2. Right? That's it. That's it. Problem 5, we're looking for the vertex and the axis of symmetry of a quadratic function. negative 2x squared minus 4x and plus 3. To find the vertex and the axis of symmetry, we need the complete square. So it's like the following stuff. So it's negative 2, you factor out the negative 2, you get x squared plus 2x. All right? And plus 3, you just add plus 3. Check here. I only factor out 2 from the first two terms, from x terms. The constant term, I do not put it in. And here, you have x squared plus 2x. If you want to complete the square, you need to add a 1. Add this 1 times the coefficient is a minus 2. This addition 1 times negative 2 is a minus 2. Minus 2, you need plus 2. All right? So this number 2 is balanced, is cancelled with this 1. 1 times negative 2. So it's negative 2x plus 1 squared and plus 5. What is the vertex? The vertex is negative 1, 5. Be careful, vertex it must be x minus h. So here's x minus negative 1. So it's negative 1 and 5. The axis of symmetry is x equal to negative 1. So this number will give you the axis of symmetry. But axis of symmetry must be an equation, not just a point or a value. X equal to 1 represents a vertical line. All right? So this is not a point. You must write in this form. You just put the number 1 is not correct. Problem 6. Form a polynomial of function whose real zeros and the degrees are given. All right, so zeros, you have, we just need 1. We just need 1 polynomial. Find a 1 polynomial, form a polynomial. Zeros, it has 0, negative 1. Have multiplicity is 1, so here. And 0, 3. Multiplicity 2. Okay? And the degree is 3. Here's degree 1, here's degree 2. So the sum is degree 3, and that's it. And that's it. Okay? Okay, so here, by the way, if I just ask you to find 1, I only say find 1 polynomial with satisfying the property. You can do the following. If I modify the problem a little bit, we have zeros, for example, negative 1, multiplicity 1, 3, multiplicity 2. If I say degree, here the degree 3, then 2 plus 1 is 3, so you don't add anything else. If I put degree is 5, a very large one, how do we form it? You still do the first x minus negative 1 power 1 because multiplicity is 1, x minus 3 powers 2 because multiplicity is 2, and here's a 1, here's 2, sum is a 3, but degree is a 5. You miss 2 degrees, you just put x squared. You just put x squared. You can actually put whatever quadratic polynomial. I only need a square because 2 plus 2 plus 1 is equal to 5. And this satisfies the condition. I don't say it's unique. It's just one of them. Again, it's just one of them. I don't ask you to write the general formula. All right? 7. Determine asymptotes. We have fx equal to 2x squared plus 3x minus 5 over x plus 2. Asymptotes, you may have horizontal, oblique, or vertical asymptote, but you have to factor the numerator and the denominator first in order to see if you have cancellation or not. So with the cross multiplication, I can factor the polynomial in terms of 2x plus 5 over times x minus 1. This is a cross multiplication. 2 times negative 1 is negative 2. 1 times 5 is 5. Addition is 3. 3 is exactly the coefficient of x term. So, and x plus 2. So nothing can be cancelled. There's no cancellation. Then we will see that x equal to negative 2 is a vertical asymptote. Is a vertical asymptote. Okay, TOT, yes, TOT. The zero of the true zero of the denominator will give us the vertical asymptote. And this example, the degree of the numerator is greater than the degree of the denominator by 1, exactly 1. So it will have a slant oblique asymptote. So how do we find oblique asymptote? We do the long division. So we divide 2x squared by x. So 2x times x is 2x squared. 2x times 2 is 4x. And then you do subtraction. And then you divide negative x by x. You do subtraction. So by this long division, fx is equal to 2x minus 1. It comes from here. Plus negative 3 over x plus 2. Negative 3 is a new numerator. X plus 2 is still the denominator. With this result, y equal to 2x minus 1 is an oblique asymptote. And that's it. This rational function will have a vertical asymptote and a oblique asymptote. It does not have horizontal asymptote. Okay? All right. So next, we're going to show the summation of the first n integers by the mathematical induction. So we're going to show that 1 plus 2 plus 3 plus up to n is equal to n plus 1 over 2. So how do we prove that? By induction. For n is equal to 1, we're going to show this is a formula. So before we finish the proof, we don't assume it's right. We just get the target. For n equal to 1, we will check the left side. The left-hand side is just 1. It's just 1. There's no addition. And the right-hand side is, okay, n is a 1, so you get a 1 times 1 plus 1 over 2. 1 plus 1 is 2. 2 times 1 is 2 over 2 is 1. So left-hand side, you separately compute is 1. Right-hand side, you separately compute is 1. So left-hand side is equal to the right-hand side. The result is verified or is checked. We only check this formula for one case. Now we will say assume for n the formula is correct. Okay, n or n equal to k. Let's say for n equal to k, the formula is correct. N equal to k, the formula is correct. What does this mean? It means 1 plus 2 plus 3 plus up to k. I only know up to k. It is equal to k times k plus 1 over 2. K times k plus 1 over 2. All right? Then for the next one, for n equal to k plus 1, for n equal to k plus 1, for n equal to k plus 1, still we don't know if this formula is right or wrong. So we can only check the left-hand side. We're going to add up to k plus 1 because n is k plus 1, so you will add up to k plus 1. This is the left-hand side. But you see, this one, 1 plus 2 plus 3 up to k, we already assume it's right. So this long sum can be written as a k times k plus 1 over 2. So we apply our hypothesis. This is the hypothesis. So the sum of first k integers is k times k plus 1 over 2. And then we add the next one. Right? We already handled the first k numbers. And then we're going to handle the next one. Next one, let's see, we factor out k plus 1. So we will have k over 2 and plus 1. K over 2 plus 1, well, this is 2 over 2, right? 1 is 2 over 2, so it's a k plus 2 over 2. If you want to write, it's a k plus 1, k plus 2 over 2. So this is left-hand side. It's finally equal to this. All right, now let's check what is the right-hand side. Right-hand side, n is a k plus 1. So let's just check n plus 1 over 2. So k plus 1, and k plus 1 plus 1 is a k plus 2 over 2. You see? From two separate sides, you do have the same result. So the left-hand side is equal to the right-hand side. All right, so we verify the case when n is equal to 1. By assuming when n equal to k, the formula is correct, we can push one more step, one step ahead, get k equal to n plus 1, k plus 1. The left side is equal to the right side. Then by the induction or by the mathematical induction, the formula is correct. Or is checked for all integers, for all natural numbers. All right, so it becomes a solid formula. This is a mathematical induction. Mathematical induction must have 3 steps. 1, k plus 1. All right, so number 9, we are going to identify the interval in which the function is increasing or decreasing. All right, so we have function fx equal to x plus 3 squared plus 4. This problem, I think it's not right, very clear. Possibly it's like the following case. So first you have x plus 3 squared plus 4. What is this function? This is quadratic function. Quadratic function, it has 1, 2, 3, 1, 2, 3. It has a vertex -3 and 4. X minus -3. It's -3, 1, 2, 3, 4. -3 positive 4. This is a vertex. Because the coefficient of x squared term is positive, it's open up. The axis of symmetry is x equal to -3. So it's like this. All right? It's like this. So fx is decreasing where? On the left side of -3, on -infinity to -3, increasing on -3 positive infinity. On the right side is increasing. And on the interval 1, 3, where's 1, 3? 1, 2, 3, 1, 3, here. Here, if you check that, it's here, it's this part. So on 1, 3, fx is increasing. Right? You just check the graph, it go up. So it has to be increasing. This is a general property. This is a property on the specially selected interval. Right? Okay. Problem 10. Problem 10. List each real zero and its multiplicity and determine whether the graph crosses or touches the x-axis. Okay, so x minus 5 cubed times x plus 4 squared. So 0, 0, 5. 0 is a 5, multiplicity 3, right? X minus 5, so 5 is 0. Multiplicity is a power 3. Here, x plus 4 is x minus negative 4. Negative 4 multiplicity 2. Here the power is 2, so it's 2. So the graph crosses the x-axis at x equal to 5 and touches the x-axis at x equal to negative 4. When the multiplicity is odd, the graph crosses. When the multiplicity is even, the graph touches x-axis. So that is a property. Whenever you see the odd multiplicity, graph will cross. Whenever you see even multiplicity, the graph will touch. This is cross. This is what we mean touch. Even more correct word means that the tangent. But here it just means touch. This is cross, this is touch. All right, this is problem 10, and problem 11, we're going to draw the graph of the function fx equal to 3 over x squared minus 4. Okay, so the function is fx equal to 3 over x squared minus 4. So 3 over x squared minus 4. We're going to sketch the graph of this function. We need the intercepts, asymptotes, and so on. So the intercept means you have x-intercept. X-intercept y is equal to 0. So it means fx, which is 3 over x squared minus 4 equal to 0. This one has no solution because a fraction is 0 if and only if the numerator is 0. 0 over whatever stuff, non-zero number, is equal to 0. But here you have 3. So there's no x-intercept. Y-intercept. Y-intercept, you just check f0. F0 is x equal to 0. 0 square is 0. Minus 4 is negative 4. So it's negative 3 over 4. Negative 3 over 4. It has just one intercept, y-intercept. The asymptote. This fx is 3 over x squared minus 4. It can be factored as x minus 2 times x plus 2. The difference of square. A squared minus b squared is a minus b times a plus b. So here a is x, b is 2. 2 squared is 4. Okay, so there's no cancellation. You can see that the vertical asymptote there are two vertical asymptotes, x equal to, x equal to negative 2. X equal to comes from x minus 2. X equal to negative 2 comes from x plus 2. All right? And the horizontal asymptote, horizontal asymptote, you check here, you let x approach infinity, very, very big. When this x squared, x very big, x squared is big, x squared minus 4 is also big. 3 over a big number, 0. 3 over a huge number will be 0. It's almost nothing. So this is a horizontal asymptote. Now let's try to sketch. Vertical asymptote, 1, 2, 1, 2. This is a vertical asymptote. Vertical asymptote. Horizontal asymptote, this is horizontal asymptote. Okay, and x-intercept, nothing. Y-intercept, negative 3 over 4, negative 3 over 4. Now let's try to sketch it. So this is 1, 2, 3. Let's check. I don't know how to sketch it, but let's check 3. 3, F3, what is F3? F3 is 3 over 3 minus 4. Okay, yeah? 3 square minus 4. 3 square is 9. 9 minus 4 is 5. So 3/5 is here. Okay, and remember, vertical asymptote just means the graph will be close to it when the x close to number 2. And horizontal asymptote means when it is close to infinity, very big, the graph will close to the horizontal asymptote. So the graph will be more or less like this. You don't have any knowledge, additional knowledge so far, so you cannot draw the wave. Whenever you have a wave, there's always a reason. If you don't have a reason, just draw the simple curve. Don't make wave crazy line. That's impossible. All right? And also you see here, this you can only go up, you cannot go down. I say when x is approaching 2, the graph will close to this vertical line. You cannot go down because you see here, if you go down, you will have x-intercept, but you don't have x-intercept. So you can only go up, you cannot go down. All right? And for this one, remember that when x is close to 2, you have to close, the graph will be close to this vertical asymptote. Again, it cannot go up because if you go up, you will have a cross, have a 0. That's impossible, so you can only let it go down. And here is a similar thing, you can only let it go down. And then you can check negative 3. It's also 3/5. So it will be more or less like this, always. Okay? And by the way, this function is an even function. Why is even function? Even function means f negative x is fx. Even function, then the graph is symmetric with respect to the y-axis. So this is also makes sense. Don't cross x-axis. Whenever you cross x-axis, you will have x-intercept. Okay? Don't make crazy wave because you don't have any knowledge to support those waves. Whenever there's a wave, there's a reason. All right? You just use a simple curve to connect them. Okay, excellent. I finished the whole argument. I hope it is helpful. If you have any questions, let me know, okay? If I make any mistake, also let me know. I will try to correct it as soon as possible. All right, thank you very much.